Hi, so this talk is about secure building blocks. So secure building blocks, nothing but it's a modular block which can provide end-to-end solutions in a embedded system or any system. It can be secure boot, secure update, secure communication, secure process, or secure storage. Okay. So it was our goal to build something which can be plugged and placed in your code very easily. It can be get into the existing stack. Okay, and it can be fast, secure, and it can update very fast based on your security vulnerabilities. Maybe today this cryptographic algorithm is safe, tomorrow it will not be same. So how much fast you can update the code? Okay, we need to have a updatability in your code. So we're looking into all these aspects. We wanted to select a language. Okay, now step was we selected our secure building block. Obviously it's open source software development. We wanted to go for a language. Which language should we choose? So we had multiple options in our head, maybe C, C++, Rust, Go, okay, Python. Okay, we have multiple options, but of course we have boiled down to 2 to 3 options: C, C++, Rust, because they were systems level language which can have high performance because they don't have GC in it. Before you get into the Rust world, right? You have to justify yourself why are you using Rust, because there is so much of stack available, C and C++. So justify yourself and everybody, because so legacy of code is available. You just can't go and change it. So we did some evaluations from our side. We also saw some papers. Okay, so why Rust for embedded system development and by extension automotive software security? So and embedded system is one thing that can come where automotive, IoT, medical, anything can come there. Okay, embedded system is a very vast thing. So Rust can go in everywhere. So how can by extension give automotive security? Okay, automotive is one of the important aspect area where security is very important, where which any very little here and there could lead to very high disaster. It can be space technology, it can be anything. So we wanted to see if why should we if is it compiler is reliable, is it certified? We have to see so many options. Okay, when you go for a new language, getting into the automotive world where tried and tested software is already running in a field. So yeah, so okay, we have taken Rust, but what is it about? Okay, it has fast. It is very fast because there is no GC. There's no GC. So obviously the performance is very high. Then low memory usage. So there's no runtime or VM, and it compiles down to a machine code. Okay, so obviously there's no bytecode available directly. You're gonna get a hex file which is binary, which can directly run on your controller as a bare metal code. And it also has memory and concurrency safety. Okay, no use of free dangling pointer, null pointer, and data races and all. So this is one of the very good thing in automotive when you have a fearless concurrency kind of concept which is available directly. But the name is a fearless concurrency. It's very useful in your they can use it. Okay, and the powerful type system this is the one thing what Rust people like. The type system is so great that you can have your custom types, and that custom types can be matched from your match statement or can be handled error. So it will help you to have a clear flow of data in your code. Okay, if something is not happening, come out pattern matching, error handling, safe multi-threading. Okay, all these are powerful type system, which combination makes it superb. Along with it, we have excellent tooling. We have a Rust of one single tool, one single compiler, not like multiple single things, and documentation is so nice, so good. The community is built such a way that seeing the drawbacks of few previous legacy of code, they thought okay, documentation should be must, because today whatever code you write, tomorrow you have to be able to identify what exactly I wrote. Okay, if you're not unable to identify, then it's a loss of time. You have to read from the beginning. Unified build system, dependency management. Okay, all these are reasons. Then we have so along with it, it gives a modern general purpose programming language that also has these many features. Okay, so then it has the necessary ingredients to produce a safe, reliable, performance systems code. So you have a safe, reliable, performant code. So what do you want? What else do you want? Still, you're not stopping. Okay, we got from our answers looking into the Rust thing, and we will see what is available, what data do we have. So an existing code base. So Chromium security, we went through a couple of projects, and there are so many available online. We tested ourselves, some we read. Okay, The column safety, the memory safety. So around 70% of high severity bugs are memory safe bugs. So memory safe bugs are the highest bugs. So 2021 memory unsafety, Apple's operating system 14 had 60.4% of memory vulnerabilities, 13 had 59.4%, 12 had 66.3%, 11 had 60.5%. This is a very huge number. Android developers blog, the queue, the hardening enhancements, use after free integer overflows, out of bound reads, writes, compares 90% of vulnerabilities with OB being the most common. These are the things which is not properly managed in the existing code base. Okay. Then also we saw the project zero. The memory corruption issues are the root cause of 68% unlisted CVs. So we know that the memory safety issue has become one of the important factor in our security software development. So we have to completely eradicate that. Okay. So we were unable to completely eradicate memory safety issue from any existing language, maybe C or C++ or Go, Python. Okay, we have done in our evaluation, nothing could actually completely remove it. So Rust is a language which will make you write a memory safe code. If you know Rust, it means the code whatever is going to compile, it's for sure is memory safe. As a guarantee it gives you. Then we saw what exactly it is providing. So safe memory management and powerful type system. These are the two things, the two combination which is giving you everything, automotive security or software development. So what does it give? It gives three main things: safety by construction, zero cost abstraction, compile time checks. Okay, so what does safety by construction means? Pointers are set at compile time. So all the pointers, unless you don't put in unsafe block, everything is safe. You can't just go and access some location and write something into it. Thread or task safety from types, no hidden states. Zero cost abstraction, efficient zero cost generics. So if you can also define a marker traits which will not take any memory. No GC at runtime, safe and unsafe Rust. Compile time checks. So compile time safety analysis. So unless you don't have a dynamic dispatch, you're gonna make every single code compile time check. Trait based conditional APIs, control allocation and dispatch. So these things makes safe performance and fine grain control of a system. This powerful thing will help you to have a memory safe code. You can stop it. With Rust safety guarantees plus powerful type system, embedded systems program can write complex software that's safe. Now you can write a complex software which is safe from our Rust. How can Rust help in automotive systems or software security? So we saw that Rust can give you a safe and perform high performance code which can help you write a complex code. Okay, now we can write a complex embedded system code. But how does it help in our automotive software security? Then we have our something called as some more points we have. The Rust greatly helps functional safety. Okay, so Rust guarantees memory and concurrency. So memory corruption vulnerabilities are impossible apart from compiler or a hardware malfunction. So there is no way possible that you're gonna have memory corruption issues in Rust. Okay, if it's happening, it's because of compiler or some hardware malfunctions. Okay, all shared mutable state is unsafe. So anything which is mutable state is unsafe. No race around conditions due to send and sync traits. So if you just go into the threads part of Rust where you can see how you are trying to access a variable inside Automix, you're going to lock it, other thread will unable to access it. The way it is designed, send and sync. If a type implements a send, then you can pass the mutability to it. If it implements a sync, then you can share it. Okay, so everything is completely types and traits here, which will make the whole code very clean and understandable and memory safe. Exploit by default, pub, mute, clone, result propagation, casting are beneficial. And also we have some formal verification tooling called any, Rusty, Miri, etc., which will help you to test your model code like functional basis, model basis, system basis. We can test it step by step. Also, you don't have to follow the MISRA C standard what you actually follow in C, right? Because any code you write it's memory safe, and it is compiler will make sure that everything is followed, because you're trying to write your own memory management in Rust, which is not there in any other language. You're basically managing the whole memory. You're trying to access the stack memory. You're not trying to access any heap memory here. The soundness compiler can verify the absence of undefined behavior. The compiler can actually verify the absence of undefined behavior. Okay, that's the main thing, which all these factors, along with it, we're also having some compiler releasing this October, which will make Rust a suitable software for embedded software development. And a security team, we take it as our main building block. We our first 70% of issue memory safety is solved by one language. Okay, so we take Rust as our main code, main software, main language for our software development. Now let's get into SBB. So SBB stands for secure building blocks. So as I told, there can be multiple existing code available. It can be in automotive. You just need to have a linking codes or a modules in between those code, so that you don't have to change the whole entire code. Just wherever security is required, go place it there. That is when our secure boot will come, which will help to securely boot your firmware or update your firmware. Then you have something called trusted firmware, where you sign the firmware and you tell that, okay, this is a genuine firmware, what I'm sending it to you, and the verifier will verify it. And you have a trusted identity secure authentication. So we're going to have elliptic curve cryptography, and this code is designed such a way that, example, today this curve is broken, tomorrow we're going to have some different curve. So it will help to have also have post-quantum cryptography algorithms also in our system, such a way it is designed. Then we have secure update. So once the code is firmware is verified, so if you have any update available from FOTA, when you do FOTA, so you're gonna get the firmware. It'll be in some location. How do you verify it and how do you update it? This is about one aspect. Then you have a cloud available. There is some data available in cloud. How do you communicate it securely from your device and a middle device? So, and if you want to process some data, how do you process it securely within the system? Or you want to store it in somewhere securely, how do you store data? So all these are the small blocks, building blocks of our building blocks, which will help you to make the whole system secure. It can be trusted, secure authentication, rustboot, secure update, trusted firmware, secure communication, secure storage, secure process. Okay, and everything is modular. So modular building blocks to simplify security development lifecycle. What is it? So what do you benefit from that? The benefit what you get is faster go to market, and also you can also keep on updating your code. Impact: reduced operational risk, independence from vendor lock-in, reduced trusted computing base, guaranteed memory, data race safety, minimize integral complexity and boot time, avoid vendor lock-in. These are some of the benefits what you get when you have a SBB. So this project is completely open source. You can find in my GitHub page, Yashwanth Singh, which is just my full name. You can also scan my QR code, my first slide. Slides will be given, I believe. So you can find this project is completely open source. So now we have built something called as secure authentication, secure boot update. So these are blocks are already available. The reason why we make open source is because we need more contributions to it, so that many people can put their own ideas and build a software. When everyone collab, and we're gonna make a very strong software out of it. Next, IoT security. So if you see the architecture of your system, right? So you have a hardware layer here. This is the MCU, and this is for a Linux machine. Basically, this is for MPU, microprocessor. This is for microcontroller. So if you have a microprocessor, then this architecture will follow. Controller, we have a architecture. So whatever is a white thing is basically security component, security accelerators are available here on the hardware. Hardware can be anything. Then you have a trusted execution environment abstraction layer, which will help you to talk to this hardware, proposal, accelerators, etc. And then you have your firmware upgrade and secure boot, which is in your green layer, what we are developed right now. And then we have our crypto cell library, secure storage, key storage, certificate management. All this comes in the above layer. on that application sits. Those are the bare metal things what we want to do on our MCU. On MPU, the same thing. Trusted execution environment, abstraction layer. Because here you're gonna have your kernel and drivers above the hardware. Then you have a networking stack, secure transport layer, and then application. Those are typically you're gonna have your blocks designed on your hardware. Then we have our digital signature. The key component of secure software development is digital signatures hashing. So we follow something called as asymmetric cryptography, where you're gonna have private key and public key, which is different. So private key is with the person who is signing the firmware. Maybe a person who is producing the firmware, a developer has a private key. Controller will have, or the device which is client device, which is in the field, will have a public key. The private key is used to sign or digest of firmware image. Okay, private key is very confidential, by the way. Public key is used to verify the signed digest. Can be shared publicly. It can be shared. Anybody has public key can be shared, and whoever has public key can verify it. But private key is confidential. If you lose it, then it's gone. So data is something. It can be firmware, it can be data. You take a hash of it, and you're gonna get digest from it. So what is digest? Digest is something of fixed value or a fixed data bytes. Then you're gonna encrypt it. Then you're gonna use a private key and you're gonna get a signature out of it. Okay, so data, you're gonna hash it, you're gonna get a fixed size, and you're gonna encrypt it along with the private key, and you're gonna get a fixed size signature. So basically, it's like a piece of paper. You're signing it. Okay, on a piece of paper, if you sign it, it becomes a document, or it becomes your property, something like that. Okay, the signature is out of your data, which you're producing uniquely for a particular firm or data. Now at booting time, how do you verify it? Okay, the signature, whatever you have signed, will be available on your firmware or on a piece of paper. Okay, so how do you verify with the data? So now now in the booting time, the firmware again, the bootloader is gonna hash it, and it's gonna get the digest of it, and you're gonna take the public key and decrypt it, and you're gonna get the digest of it. So you're gonna get these two digest, and you have to compare it. If it compares successful, then you're gonna get if the booting is, you're gonna verify it, and you're gonna go for next step. Okay, that's how private key and public key. Private key, I'm gonna sign it. Public key, I'm gonna verify it. Hashing is required because to get a fixed length of data. It's called digest. Then we have something called as this is a flow typically. So ROM code is something which just serves as a root of all trust. Okay, ROM code is a code which is immutable. Immutable code stored in some form of onboard non-volatile memory. It is flashed at your manufacturing time. ROM code is the first piece of code to execute. So ROM code is the first piece of code that executes, which will do the signature verification of a bootloader, which is just first stage bootloader. Our trust of anchor is public key embedded within the ROM code. So we have public key in our ROM code, which is our trust of anchor. ROM code serves as root of trust. In practice, it is stored safely in something like a one-time programmable fuse. So it is inside your one-time programmable fuse, in what's called OTP. Integrity of trust of anchor is important, not confidentiality. Integrity is important. Okay. So next we're gonna have the next public key, and then a verification. The kernel will be verified, and digest will be verified. Hash verification. Then it goes to root. These are the control flows. Every component is verified using digital signature and public key. Next comes our rustboot. So this talk is mainly focused on how do you boot a firmware, how do you sign a firmware, how do you verify it, and how do you update the firmware. Okay, these are the things what we're gonna cover in our session. And the remaining secure communication, secure process, secure storage is a different topic itself. So boot itself is a one topic. So we're going to take introduction of secure boot, and what are our goals, and what are the features we are offering, architecture, what's the flow of booting sequences. So all this we're gonna see. You can actually scan this QR code and you can get the Rust book. It's an open source book we have written. So if you want to have a bootloader for your MCU, then you can read this book follow instructions, and you can have a support for your controller basically. Okay, so what is Rustboot? Rustboot is a standalone bootloader written entirely in Rust, designed to run anything from microcontroller to system on chip. It can be used to boot into bare metal or Linux. It's a technical definition of Rustboot. It's a secure bootloader basically. Rustboot, just a secure bootloader, nothing more. Bootloader, help to boot. Okay, how it is different from other bootloader, we're going to discuss it. We're going to see it. Okay, it's very small, tiny performance, high performance, etc. etc. Okay, so what are our goals when I'm building a bootloader? Okay, compiles with key requirements of IETF tool standard. Okay, so whenever you design a bootloader, right, you don't need to have a whole network stack, the flashing UART stacks, all the protocols in it, because you're not building OS. You're just building a first stage of bootloader, which has capability of verifying the next stage. Okay, so you are gonna have network stage, network layer, everything. This should be in your application like code or your firmware. Bootloader should not have all this headache. Okay, so if you increase the size of your bootloader, you're gonna increase your attack surface. Size means you're gonna adding more and more features to it. If you're gonna add a USB feature, or you're gonna add some UART feature or some protocols feature, network feature, attacker gets 100 ways to go into it. So we're gonna minimize it. Okay, required peripherals we're gonna use it. Okay, we will not even use UART unless it's necessary. There's not going to be any protocol interface from external world to tamper it. Unless you go into memory using a JTAG or something like that, there's no way possible you're going to get access to it. Reliable updates. Also, your bootloader should be updatable. See, today you have a electrical free 256, NIST 256. Tomorrow it can break. How do you make sure that your bootloader is updated? Hardware can stay for hundreds of years, but your software has to be updated every single time. How do you make it? So our goal is to also have a reliable updates. Predictability of performance. Performance is fine. Okay, it is very fast every single day performance. But how much predictable it is? Today it is behaving like this. Tomorrow also, are you making sure it is behaving like this every single day? So how do you make sure it? That's called predictability. Zero dynamic memory allocation. So how do you make sure that your bootloader is having no heap in it? Okay, we don't want any dynamic memory allocation in your bootloader. That's the fourth point. Fifth point is the most important point, which is memory safety and type state programming. This is completely offered from our Rust itself. Okay, so there are some features like predictability of performance, zero dynamic memory allocation, and Rust safety and type state programming. All these are features are directly available from Rust. The top two features are available from maybe first feature is available the way you design the software. The second is how much modular you're gonna make to get reliable updates. Then we go into our features. Okay, this is what goals we have. So whatever features, whatever we have offered. So currently our Rust bootloader offers support for ARM Cortex-M and Cortex-A MCUs or microarchitectures. So we support different family of controllers like STM, microchip, and RF. Many people have added support for us as an open source project. Support for multi-slot partitioning of flash memory. This allows to implement boot update approach for bare metal firmware. So we're gonna have a flash. We're gonna make it partition the flash, which I'm gonna go in detail in the coming things, where you're gonna have boot partition, update partition, and swap partition. Support for ARC64 Linux supporting. So we have also support for ARC64 right now. It's the only architecture what we have Cortex-A support. Elliptic curve cryptography for integrity and authenticity verification in crypto crates. We're gonna also add post-quantum crypto to it. Tiny hardware abstraction layer for non-volatile memory flash access. So I told you we're gonna have very tiny HA layer, flash layer, so that we're gonna make our bootloader very less memory, so that we're gonna have high performance. Anti-rollback protection over version numbering. So if there is any while booting the firmware, if there is any power gone, okay, we're going to roll back to the previous firmware. Or if authentication failed, we're going to roll back. So we're going to have a rollback facility also in our firmware. Fully memory safe bootloader, core bootloader implemented with safe passes and firmware update logic. So it's all about how we design. So we have a lot of, it's not only Rust which is offering the safety. Of course, it offers 70%. The rest 30% you have to offer it. So how are you making sure? So you're going to use parsers and firmware update logic. The power interruptible firmware updates along with the assurance of fallback ability. So power interruptible rollback is available. Switch to Rust-based signing tool. The key features firmware signing to improve scalability and security. So we have written our own firmware signing tool, which will help you to produce trusted firmware. And we are also using trusted authentication also there. So everything is written from from scratch. Okay, support for external flash devices. Or apart from this, we also support something called as trusted execution. We have also given support for ARM trust zone thing, and which the PR is on the way. So we support various families of controllers, like as I told, NXP, STM, NRF, RPI, and ESP, things like that. Also, we are adding support, and we also have the Cortex architectures like M0, M4, M7, etc. like that. So every single architecture we're trying to cover it. If you want, feel free. If you have to add support for your controller board also, you can go from our Rustboot book and you can follow the steps and you can add to it. Then we have architecture. So in our architecture, we have two main stages. One is called pre-handover stage, other is called post-handover stage. The design is based on a simple idea. A bootloader handles only a bare essentials and offloads the rest of the system that is better suited for a job. So any bare essential requirements only will be in our bootloader. Rest all things will be given to your controller. Okay, there are two main things here. One is the pre-handover stage, other is the post-handover stage. In the pre-handover stage, we're gonna have the boot ROM. So basically, boot ROM is a guy which is a bootloader available on your ROM, which will give the handle to the bootloader. Some other intermediate stage bootloader executes and hands over to our Rustboot. This is a stage where Rustboot has full execution control. So pre-handover stage is where the boot ROM give control to your Rust bootloader. And then you have your post-handover stage where firmware has begun execution and has counted execution control. The firmware uses couple of Rustboot dependencies to trigger and confirm the updates. So pre-handover stage is when the boot ROM will give control to your Rustboot, and Rustboot has a complete control. And the post-handover stage is where the bootloader will give control to your firmware. So this is how the flow works. Let's get into our pre-handover stage. So pre-handover stage, we have a couple of things here. So we have a Rustboot core bootloader. It has an embedded public key. So embedded in software or in hardware. It depends on the architecture. So if you have a crypto accelerator, something like that, we can keep there. If you don't have any cryptographic hardware, then you can keep embedded in your software itself. Okay? There are two ways available. So this is your hardware, MCU or MPU. On that you have your HA layer, which is your hardware abstraction layer. So we're gonna have only bare minimum things. We're gonna extract it. Maybe UART, GPIO, flash, and crypto peripherals. Okay, only these things we're gonna make it available. We're gonna make the code as small as possible. The next is Rust crypto. So basically optional software-based crypto library. So if you have a hardware available, go for it. If you don't have, you can use the Rust crypto layer, which is a third-party layer, which is proven, and we're going to take it. We're going to take and we're going to use it, which will help to your verification of your firmware. This is your basically a pre-handover stage where Rustboot will have a complete control. Okay. Then we have our post-handover stage where your application will have a control over it. So secure element hardware is here, Linux or bare metal. So bare metal firmware is here. You have your networking stack available here, and there are some Rustboot APIs. So now the control is gone to your firmware, but there are some APIs using which you can talk to your bootloader. Okay, Rustboot provides a tiny API to trigger and confirm updates. So if you have any update available, how do you confirm it? It's available in your Rustboot API. Then you can download and install your app and trigger update. This is basically in your pre-handover stage, you're going to have the Rustboot complete control. In post-handover stage, you're going to have the firmware complete control. So So basically, signing means what is signing? What exactly signing means? So you're gonna have the firmware here, and you're gonna put 256 header over it. So how do you do it? So you have your image. So this is your 256 byte header. What you gonna attach it to your firmware? So you have your firmware. You're gonna attach a 256 byte header, which will make a signed firmware. So how do you make a signed firmware? This is a technique. So you have your firmware. So Magic and EOH are basically header and footer. What you're gonna add? It can be anything. So we're adding Rust and boot here, just like that. Then you have image size. How big is your image? Then you have a type length value. So for next piece of thing, what is the type, what is the length, and what is the value? And we're gonna have some padding, and we're gonna have type length value again, which is type length value for a next field, which is a timestamp. So timestamp is nothing but of at what time you are compiling your code. Then you have something called type length value for image type. So what is the image type you are having? It is a boot image, update image. So that information will be given here. Then again you have padding. Then again you have type length value. Okay, so now till here we have information of our firmware. So we're gonna take all this information and we're gonna produce a digest of it. We're gonna hash it and we're gonna get a digest of it, which is 256 bytes. And this 256, okay, we're gonna have a fixed SHA-256 by 256. Sorry, we're gonna have fixed SHA-256 bit digest, which we're gonna store here. Then we're gonna have a TLB, and whatever public key is embedded in your bootloader, we're gonna take the digest of that also here. So we're gonna do everything verification. And now we're gonna have a TLB. We're gonna take everything and we're gonna make a signature out of it. We're gonna take a elliptic curve and we're gonna do some manual operation. We're gonna get a unique number, which is called a signature, and that will be stored here. And all this thing is called a header, which is responsible for a name of a signed firmware. We take this and attach to a firmware. We call it a signed firmware. Okay, so this is your signed firmware. This will be sitting in your boot partition. So we're gonna take the signed firmware and we're gonna put it in our boot partition. Rustboot is a bootloader which will go and check every single byte of your header. If it is verifies, then only the control will be passed here. Else the bootloader will be here. So Rustboot will go and check every single thing. So this firmware will be sitting in your boot partition. This will go and check every single thing. If everything is verified, okay, then go ahead. The control is going to boot firmware. And next, if you have a update available, so now boot firmware has a capacity to download the firmware. So we are offloading all the network stack in your boot partition. So now this boot partition will update this example, you have a update available. So it's going to download and keep the update here. Now the trigger, again the control is given back to bootloader. So bootloader will now go and verify the update partitions firmware. If it is verified and valid, then it's going to swap the firmware. The boot going to come here, the update going to come here, and boot going to go here, and we'll start the boot firmware execution. This is how the cycle goes on. If you have update, swap it and get it. So bootloader's job is to verify the boot firmware. If any update is available, then boot firmware will give control again to bootloader, and again, so the cycle goes on. So boot firmware, update firmware, then again next update firmware, next update firmware. The swap partition is used to just swapping your firmware. This is your flow basically. So let's go into the flow chart. So whenever the bootloader start, right, it's gonna open the partitions. Okay, if it is initially it will be false, right? So it means it's only the boot partition. Then go and check for any update. If it is not there, false, then go boot in new state. Then again check it. Then verify the integrity and ability. Then, or if it is false, then panic it. Or if it is true, then update available. Then jump to rustboot. Open all partitions. Okay. Then verify authenticity integrity. Then if it is false, panic again. So this is basically a flow where you actually the rustboot loader will follow some steps, which is there here. So at the end, if it is booting is there, so rollback, if there is any rollback available, trigger here. There's a complete flow of your rustboot loader, which will be followed in your complete process. So if you have a update available, go for update and come back. So we have a couple of flags here called as FF, called new state, and 70 called updating state, and 10 called testing state, and 0 called tester state. So there is a flag what will be monitoring. So based on that flag, the bootloader will be verifying it. Okay, so if you have a boot it. If you have update it. If you have some other thing, just go and discard it. This is what the flow is about. So today's talk is mainly focused on rustboot and how do you sign the firmware, and from where do you sign it, and how the execution goes. So this is all about today's talk. So maybe next talk we can go ahead with the secure execution, secure process, and secure communication. Yeah. So thank you for your time. So you can always reach out to me via my LinkedIn. You can scan this QR code, and you can always reach out to me for anything. So my this SBB is an open source project. As I told, it's available in my GitHub page. You can find my GitHub page in my LinkedIn, or my GitHub name is just Yashwanth Singh Yam with no spaces. If you type this, you're gonna get my GitHub page. So I work on multiple projects. I work on assembly level language. I work on RTL coding, Rust, C, C++. I mainly work on some low level coding stuff. Okay, but I also have experience in high level coding, but I have restricted myself for low level coding. So there are a couple of projects which I work in free time. Or everything is available as open source. We have different sensors. So Rust is what we're exploring from past 2 years. I have a lot of projects available in C. So please do go and check it. This is my LinkedIn page, and you can find my GitHub from that. Thank you.